Okay, we're recording. So for today what we're going to do is EchoTrains. So what this assumes is the main lecture, which I'm giving after this one, and the main lecture was about SpinEcho, and so basically, just in like a couple sentences, what is SpinEcho? So SpinEcho is you do an RF pulse, and then you wait a while, and you do another RF pulse, and the first RF pulse gives you an FID. That's a T2 star decaying signal, and then if you wait the same amount of time after that second pulse, if the second pulse, so in the simplest case you have a 90 and a 180, so a 180 pulse will flip the magnetization all the way down like that, and so if you do a 180 doesn't give you any transverse signal because the transverse signal is in the XY plane, so you won't get a signal out of it. But if you wait that same amount of time, suddenly there'll be a signal. That's the echo. So this guy's the echo. And so what does that come from? Basically what it comes from is you've got in this, what's causing this decay is slightly different B0 fields. So you've got a range of B0 in here that's causing more decay than T2 decay. So it's causing T2 star decay. When you do another RF pulse, the effect of that is to, so this is the RF, this is record, SIG. The effect of that is to basically flip the guys who were ahead to behind. So what it does is, you can imagine some people are getting ahead because they're in a higher magnetic field. When you kind of flip them all over, the result is the guys who are ahead are now behind. And so then after a same amount of time, they'll all come back into phase. So I'll go over that in a lot more detail in the main lecture, but that's the basic idea of SpinEcho. So that's SpinEcho. So we're going to assume that now. So let's assume that and then talk about what happens if we do another RF pulse. So, EchoTrains, because typically in MRI you very rarely just do one RF, a second RF, and then you just collect one echo. That's very rare. In most cases there's a long train of echoes. In a lot of sequences, it could be as many as 100 echoes. So we have to talk about sort of EchoTrains, and so that's the topic for today. And then in the main lecture, I'll go over this in a lot more detail. Okay, so EchoTrains. What's the simplest case after 2 RF pulses? The next case is 3 RF pulses. So if you do 2 RF pulses, you get 1 echo. If you do 3 RF pulses, you get 4 echoes. So if you do like 6 RF pulses, you get 121 echoes. So the bottom line is it's actually really easy to make echoes. And in fact, the problem is too many echoes. So like I said, if you do 6 RF pulses, you get 121 echoes. But you might, in a typical sequence, you might be doing something like 10,000 RF pulses. So you're going to get millions and millions of echoes. And so one of the problems actually with MRI, one of the main problems in thinking about like how to design a pulse sequence with MRI is that you actually have to sort of deal with all these various echo pathways so that they don't cause artifacts. So the source of a lot of artifacts are all these additional echo pathways. So let's just go over the 4 different kinds of echoes that you get from 3 pulses. So 2 pulses will always give you 1 echo. 3 pulses will always give you 4 echoes. Now some of them might be on top of each other, but I'll draw them so that they're not on top of each other. So the first thing is the actual input. So here's the input that we're the RF input. Okay, so we'll start off with 1 RF pulse, and we'll call this RF pulse alpha 1. So in the MRI literature, when you use the Greek letter alpha, it often means some RF pulse that's not necessarily 90 degrees. So what is the degrees business again? The degrees business was, imagine you're in the rotating coordinate system and you've got some magnetization to start with. So that's your MZ0. And you do some kind of flip. Doesn't have to be 90, but if say you just do this flip, and so how do you measure that angle? So it's that angle. And we said that what that's going to do is that will create this much transverse magnetization. So here's MT. So that's how much transverse magnetization we're going to get. So when you see alpha, what it means is any old angle RF pulse. So special cases would be a 90. So if you do a 90, you have 0 Z magnetization. So this is the Z axis. This is the X axis and the Y axis. So you basically have, if you do all the way to 90, Z will exactly be 0. If you go all the way to 180, X and Y will be 0. So you'll have a negative Z. So it's possible to go all the way to negative. So there's another one like that. So if you do a 180, it's possible to just get negative Z magnetization and no XY magnetization. But for this purpose here, the most general case, we just have any old angle called alpha that is not exactly 90 or not exactly 180, which is the most general case. And it's very common to have a small flip. Many different pulse sequences use small flips that are not 90 and 180. Okay, so here's that pulse. So that's the RF, and then so this is RF stim. RF. We're doing RF to the sample, and then our response is down here. So here's the RF response. So this is our F record. And like I said, we could always do an RF, if we had a transmit-receive coil, we could do the transmit with the RF coil and then the receive with the same coil. Most times when we're doing brain scanning or even body scanning now, we transmit with this very big coil that transmits to the whole sample, which is you, and then you just have very local coils that pick up. But it could be the same coil also. So the first result is after that goes is we will get an FID. So the very first thing that happens is we have the signal that comes out, and it sort of like dies away quickly. So here's the T2 star. So we'll call that one FID1. FID1. So so we haven't. So you often one thing to keep in mind. You often don't record the signal directly coming off the FID. It's not uncommon to actually wait a while, do some additional pulses, and then record something later. And so you don't always record. You don't always record the FID. So that's the first one. And so then the second one is we do a second one. We'll put the second one over here. So that's another pulse at a later point in time. Could be any angle. It doesn't have to be 90 or 180. And so since it's not 90 or 180, it's actually so if it was exactly 180, then there's no FID. So keep that in mind. So if you do 90, you get a whole bunch of transverse magnetization. So 90 gives you the most. So a 90-degree pulse is the way to get the largest amount of signal. If you go past 90, you start. So if you do nothing, you get no signal. If you do a little flip, you get a small amount of transverse. If you do a 90, you get a large amount of transverse. If you do past 90, you get less transverse. If you do 180, you get 0 again. So it's pretty much like a cosine curve. It is a cosine curve. So it's it starts off big. Oh, sorry, it's a sine curve. It starts off at 0, and then you get the biggest at 90, and then you get the 0 again when you get to 180. So what will happen from the second one is another FID. So here's another FID. T2 star, so this is FID2. So if we just did FID1, nothing happens. You just do FID1, signal just disappears, it doesn't come back. So if we do a second FID, the second RF pulse, now we get one echo. So what is that echo? So that echo is going to be, so I'll draw down below here all the different times. So we need some sort of label for the time. And so this first label, we'll call that amount of time tau 1. So tau, we use tau, the Greek letter, to mean like a constant amount of time. So that's why, as opposed to t would be a variable, like e to the minus t over t2, t is a variable. Here tau is just like a constant, a fixed amount of time. So what happens, I'm just going to redraw, what happened in this case. So what happens is that amount of time later, we'll get a spin echo. So here's our spin echo. So tau 1 amount of time later, we get a spin echo. And so what is this? And this will occur, it doesn't have to be a 90 and a 180, it could be a 45 and a 35 degree angle flip. That's okay too. So what will happen is we'll get a pretty big echo here. And so what will happen is, you'll see something like this. So the signal will just rise out of nothing, reach a peak, and then go back down again. So that's our spin echo. And what caused that was when we did the second flip, it flipped some of the spins over so that ones that were ahead are now behind. And then when you let that situation continue for tau 1, eventually it cancels out all the phase dispersion, the different range of different angles that develop because of this fixed magnetic field offset, B0 difference, and then everybody comes back into phase here, and then as soon as they come back into phase, well, then they continue going back out of phase again immediately after the echo. So that's why the echo dies away like an FID, because the same thing is happening again. The fixed magnetic field offsets are all fixed still, and so then they continue to just, to mess up that sum and cause that extra T2 star decay or T2 prime decay that's added on to the regular T2 decay. Okay, so that guy is SpinEcho 1, 2, because it came from pulse 1 and 2. So if we didn't do any other RF pulses, nothing would happen down here. It would just, everything would just die away. There would be no signal. But if we do a third RF pulse, so let's put the third RF pulse right about here. So if we do this third RF pulse, now we're going to get four additional echoes. So what are those 4 additional echoes? Now we've got another 2 times to consider. So which echo should I do first? Yeah, I'll just do them in temporal order. So here's another time. Put it down here. So this is, time tau 3. But that time turns out to be we haven't actually defined. Yeah. Okay. So let me get rid of this guy and put tau 2 in first, because then it makes a little more logical sense. Okay. So this time is tau 2. Okay, so that's the time. So basically, I can put them up here too. So here's the time between the first and the second, and this one is the time between second and the third. So tau 1, tau 2. Okay, so here's tau 2 down here. So then we've got a third time here, but this third time is dependent. So this is, we'll call this one tau 3. That actually just equals tau 2 minus tau 1. Okay, so here it's just tau 2 minus tau 1 that gives us tau 3. So it's actually sort of dependent on those other ones, but it's convenient to just have it as a single number, because we'll have to have a spin echo from that. Okay, so what's the first thing that happens after this? So the first thing that happens after this is another echo that is tau 3 here. So another little echo happens right here. Not a very big one. So where did that echo come from? So when we look at this, so this guy's a spin echo. This guy's a spin echo because it came from, we did an RF pulse, guys got out of phase, we flipped some of them around so that the guys who were ahead are now behind, They come back into phase. That's a spin echo. But if you look at the structure of this spin echo, it looks like we did another RF pulse, because it looks like everything's in phase at the very beginning, in the very center of the echo, and that's exactly what the RF does to all the protons. It sort of sweeps them up and gets them all in phase with each other. And so this is kind of, so the second half of this, just like RF pulse. So it's almost as if we did an RF pulse. Then we actually do another RF pulse, and this RF pulse generates an FID. I forgot to draw that in, so here's that. Here's the FID from that guy. So that's FID 3. So that guy actually does an RF pulse, and then we're going to get another one of these guys, another spin echo. So this one, the second half of this echo acts just like an RF pulse, because everybody's in phase in the very center, and then they start to get out of phase. And then we do another RF pulse, and that will flip some of these guys around so that the guys that were ahead are now behind, and then they'll cancel out all their phase errors, and then you get another echo. So this guy is called a secondary echo. So this is a secondary echo. So that's made from, a spin echo that looks like an RF pulse, and then another real RF pulse, and then you get an echo out of it. And the amount of time that it takes is exactly, the amount of time between the center of the spin echo and the beginning of the third RF pulse. And so that tau 3 later, that's when that guy occurs. So then what happens? So now we get to the one that's the hardest to understand. This is so what happens now is an amount of time equal to tau 1. So let's take this tau 1, and so here's tau 1 after this one. So it's right here. So this guy is tau 1 amount of time. So tau 1 relative to what? So what it is it's tau 1 after the third pulse. So you have first to second is tau 1, second to third is some other number that's not bigger or smaller than tau 1, and then take the third pulse and go tau 1 after that. So this amount of time after the third pulse, you get a really big echo. So there's a big echo here. And this one, I'll draw these guys. These guys should be the very beginning of them should be a little bigger. Yeah, FIDs. There we go. Yeah, so we get this other big echo here, and what is that one? So this one is called a stimulated echo. So sometimes it's just they abbreviate it STE instead of SE. So this guy is it's called a stimulated echo. So all echoes are stimulated because you can't get an echo unless you have an RF pulse, but stimulated echo just means an echo that you get out of 3 RF pulses. So whenever you have 3 RF pulses in a row, you'll get a stimulated echo, 3 real RF pulses. And what is the sort of phenomenology of the stimulated echo? Well, it's always going to be like the following. So if you do like one, so one RF pulse, and then two RF pulses, and then a third RF pulse, the stimulated echo will appear here. And if you say, if we do two RF pulses like this and put this one off, the stimulated echo will appear here. So it always appears, pulse 1 to 2 after the third echo. So what's causing this? So this one's the hardest one, but to understand. But basically, so we do the first RF pulse, and that turns longitudinal magnetization into some transverse magnetization. It's an arbitrary pulse, so it doesn't turn it all in there. It's not a 90-degree pulse, but it turns some of the longitudinal into some of the transverse, and it leaves a little bit of longitudinal. Then the second pulse. So one of the things it does is it sort of flips things around to get the guys that were ahead now behind. But there's another thing that it does. And so left over, there's still some hidden transverse magnetization. So what we're going to talk about in the main lecture, what's going on here? In this region, there's no signal. There's no signal coming out, but in fact, there's a bunch of transverse magnetization. You can't see the signal because it's all sort of spread out in phase and canceling itself. But there actually is real transverse magnetization there that real T2 jostling electrons has not canceled yet. It's just that in all the different little parts that are in slightly different magnetic fields, it's caused the phase to spread out, and so all the vectors are canceling each other out. So there's two different situations where you could get zero. You could get zero where all the vectors are really small, but in other cases you could get zero if the vectors are still pretty big, but they're all spread out, and so they're canceling each other out. And that's what's going on in this middle part here. So there's actually a bunch of magnetization left in there, but it's hidden because T2 star messed it up. So that transverse magnetization, that leftover transverse, so it's leftover MT, that's invisible. Leftover MT, invisible, is flipped into the longitudinal.
Alexa, what's the high temperature in La Mesa today?
So it's flipped into longitudinal. So you've got some leftover magnetization and you turn it into longitudinal, some part of it. You don't have to do all of it, just some part of it. Now what happens is it gets saved. So why does it get saved? Well, if you're transverse, what happens is your precession frequency is being affected by the local magnetic field. And if your precession frequency is affected by the local magnetic field, if the local magnetic field is slightly different, you're going to get out of phase. You'll go a little faster or a little slower. And so, however, if you get sort of turned into longitudinal magnetization, that doesn't happen to you, because you're in the z-axis, and so you're not precessing, and so you're not going to get out of phase. And so what happens is when you do this second pulse, whatever leftover transverse magnetization here gets stored in the longitudinal axis. And when it's stored in the longitudinal axis, it doesn't get out of phase, so it doesn't decay. And that's why the echo is so big, And then what you do is you do the third pulse, and what the third pulse will do is it will flip the saved, some of the saved, MT. So some of the flip the longitudinal, which was the saved transverse, flip some of that back into real transverse, and because it's flipping it, sort of inverting it, it's going to do the same thing that SpinEcho does. And so whoever was ahead is now behind. And so it's like a SpinEcho, except that the thing that's weird about it is that what it's flipping around isn't actual transverse. It's just transverse that was saved as longitudinal. And then when we flip it, we suddenly expose it to the transverse axis, and then that will allow us to do the same kind of thing with SpinEcho, where whoever was behind is ahead, whoever was ahead is behind. And so that's why the timing. So this was figured out just with little chemical samples, just adjusting the time between the FIDs, and you can clearly see, if I just make this time a little shorter, this echo will just come in. This stimulated echo would just come in a little closer. And they could easily be on top of some other echo. Like, if I made this a little shorter, what that's going to do is that will sort of like pull this guy on top of the secondary echo. So you might have a secondary echo on top of a stimulated echo. That could easily occur. So this is an interesting kind of method for generating echoes, because what will happen is you get a nice big echo, much bigger than this one could be as big as this original SpinEcho, but it's much later. And so if you need, for whatever reason, you need a long amount of time for something to develop, like diffusion or some other measurement that you're trying to make, this might be a good echo to use. So that's the stimulated echo. Okay, so there's only two more to go. There's two more easy ones to go, and the two more easy ones are just additional SpinEchos. So the additional SpinEchos are, if we take, the first thing we get is a SpinEcho between pulse 2 and 3. So here's two pulses, 2 and 3, and so if we just take that amount of time, so T2 amount of time over here, so that's going to be T2 amount of time after the third pulse, we'll get another SpinEcho. So there'll be another SpinEcho here. So that's SpinEcho from 2. So that's SpinEcho from 2 and 3. So this is tau 2. And then last but not least, we get a SpinEcho between 1 and 3. So if we take, so this time here is tau 1 plus tau 2. If we go that amount of time later over to here, then we've got another SpinEcho plus tau 2. So at that point, then there'll be yet another little echo there. And what is that? That's a SpinEcho made from 1 and 3. Okay, so now you can, so this is the simplest possible case after 2 RF pulses, which is 3 RF pulses. So basically, 3 RF pulses, 3 RFs gives you 4 echoes. This gives you 4 echoes. 6 RF pulses gives you 121 echoes. So how many do we do in real life? We could easily do 10,000 RF pulses. So you can see what the problem is. You've got a problem of like too many echoes. So there's an equation for it, so we could just write down what that equation is. The echo equation. So the equation is the number of echoes you get is equal to 3 to the n minus 1 power minus 1 over 2. So that's how you calculate how many echoes. So if you plug in 6 for n, you'll see this comes out to 121. So if you plug in 10,000, you'll get like a really monstrous number of echoes. So that's the well, just hold off the questions for this till the end. But basically, 2 RF pulses, we just get 1 spin echo, everything dies out. But there's a whole bunch of hidden magnetization still there. So if we do a 3rd RF pulse, suddenly these 4 additional echoes appear. And if we did a 4th pulse, we'd get another pile of echoes past that. We would get 3 to the 3 is 3 times is 27, 26. We get 13 echoes. So, okay, so how do you deal with this echo madness in principle? And so we'll just give one example of a practical pulse sequence. So one of the ways you can deal with this is, and one of the reasons why pulse sequences are often kind of symmetrical, is you want to sort of pile up all the echoes on top of each other so that they don't sort of get in the way. So, as I'm erasing, we didn't say like, what are the echoes for? Well, remember, MRI is all about recording a signal. And so if you don't have anything to record, it doesn't matter if you got some magnetization, transverse magnetization in there that's all dephased and hidden. That's no good because you can't record it. So the whole point of echoes is basically you can't get any data unless you're actually making an echo. So it's fundamental, so we didn't say what we're doing with the echoes. We're going to be doing Fourier transforms and other things with the echoes. But the whole point of echoes is if you don't have an echo, then you got nothing to record. So all the data that you're recording is always going to be in the form of an echo. Okay, so what's a simple practical pulse sequence? So here's the RF. So now we'll start off with a 90. And why would we do a 90? We want to do a 90 because a 90 will give us by far the biggest signal. So here's our initial FID. And so the equation for this is E, because it's a 90, is E to the minus T over T2 star. So that's that decay. But we know that there's a bunch of hidden T2 magnetization in there. That's the E to the minus T over T2. And so this pulse sequence recovers it. And so this pulse sequence is called a CPMG. It's Purcell was the P, my boom, and I can't remember who G was. It's 4 people. So then what we do is we do a 180. So remember a 180, if you do a perfect 180, you shouldn't get any signal because you just like the magnetization, you just completely inverted it perfectly, and so there's no transverse part. There's no XY part. So if everything works right, nothing comes out when you do that. But then if we wait that amount of time, that's just, we only have one tau now, just tau 1. So wait that amount of time, then we'll get an echo. And so here's this echo will sort of rise up out of nowhere like that. And the equation, this equation right here, will be our e to the minus t over t2 equation. So there's a lot of hidden magnetization here that you couldn't see because it was all dephased, and when we did the spin echo, it caused it to come back. But now we've still got a bunch of magnetization left. You know, even though there's no signal here, there's magnetization left. And so what you can do is basically wait tau 1 again, and then do another RF pulse. So if I do another 180 here, again, I won't make any signal, no visible signal. But then if I wait that amount of time again, then what's going to happen is I get another signal. So there'll be another signal here. So you can see there's still a bunch of hidden magnetization there. And then I can keep doing that. So if you just tau 1, so if I wait again that amount of time, do another RF pulse, wait again that amount of time, I should get another echo. So you can do like 16 in a row, quite a lot. And we'll see later on in the course you can sometimes do up to 100. So there'll be another echo down here. And this drop off here is all, so there's the T2 star, that's the T2, not T2 stars. There's the T2 drop off, but each one of these guys will be e to the minus t over T2 star. So that's a classic sequence. So why throw away all this magnetization that's still there? And when I say throw away, well, one of the things that you have to consider is that if you're trying to record something that is T2 weighted, you don't want it to also be T1 weighted. And if you don't want it to be T1 weighted, then you have to wait a long time before you do another pulse, because we want to allow all the magnetization to recover back up to the equilibrium magnetization, so there's no differences between the different tissue types when we do our RF pulse. And because of that, if you're trying to get rid of T1 weighting, you might have to wait for like 3 seconds or 4 seconds. And so this thing only lasts, a tenth of a second, and so you're going to be doing a tenth of a second, or this thing lasts a tenth of a second, so you do a tenth of a second of data, and then you just like wait for 3 seconds. That would take hours to do a scan. And so this is a way of continuing to collect data. So the data, so this is the whole signal. Typically what you're doing, however, is just recording. You throw away the FID, you don't record that, and then you just record some data points. We just record some data points here when the echo comes. And when we get to this echo, we just record another burst of data points here in this echo, because this echo isn't totally dead yet. There's still some signal there. Yeah, so basically what you can do is, get 4 times or 16 times as much data out of one 90-degree RF pulse. So if you think about this, each of these echoes are also stimulated echoes. So this is a spin echo, but it's also a stimulated echo. Because if you think about it, when you do these pulses, you've got 3 pulses here. So here's 1, 2, 3. So what you'd expect from 3 pulses is this guy, this amount of time after this pulse, you should get a stimulated echo. So this guy is is also a stimulated echo. Now, why is that? Because maybe this guy wasn't a perfect, slightly imperfect. If it's imperfect, there might actually be a little FID coming out of it, which is typically what happens. And so if it was an exact perfect 180, there would be no stimulated echo. But it's never a perfect 180, and so there's going to be some stimulated echo in here. And by arranging it this way, you avoid that echo appearing somewhere else, and messing up your data. So you have a nice stimulated echo centered right on a spin echo. So it's all about echo control. It's actually quite easy to make echoes. It's actually a problem, sort of dealing with all these echoes. They can cause ghosting and all different kinds of problems in your image. Okay, so this was a SpinEcho train. So this was a typical, what's to title this? So the SpinEcho train. You can set in the scanner interface, you can decide how many of these you want. Do I want 8 or 16 or 32? And it's adjustable. Okay, so David will stop the recording. Yes.